Welcome. This will be the first video in a series on linear programming. So today we're going to look at what is linear programming and just a couple of examples. So we're following this book, Understanding and Using Linear Programming by Jiří, Matoušek and Bernd Gärtner. It is an introduction for computer scientists. Our guiding phrase is what every theoretical computer scientist should know about linear programming. So that's our goal overall. So linear programming has been around since around the 50s. Programming here doesn't stand for programming as in computer programming, but more as in planning. So if I say this is a program for today, that's that type of programming. So you can also call it linear optimization. Historically and also today, it has been used a lot in economic applications and industrial applications. We are interested in it because of its applications in computer science, in particular for approximation algorithms. And there, next to linear programming, integer linear programming plays a large role. We're going to look at that in the next video. Let me give you a very brief history of linear programming. So it was introduced in 1939 by Kantorowicz for production planning, but his work for a while at least was not that well known. Better known was the work by George Dantzig, who also introduced the simplex algorithm. So the algorithm that also today is still the standard in linear programming, that was further developed by other notable mathematicians and computer scientists. Early applications were in the oil industry in particular, but then also in other industries. Now let's look at what a linear program is by an example. So here we have a linear program. So what you see here are the constraints. So those are linear inequalities starting in this example, and very often with inequalities that tell me that my variables, so my variables are x1 and x2, that those are non-negative. So this means that I'm only looking at the positive quadrant. And then I have further constraints. So for instance, this one, minus x1 plus x2 smaller equal 1. If you would set this to equal, then you get exactly this line, which you can, for instance, see by plugging in 0 here. Then you get x2 is 1. So this is my 1 here. And x2 equals 1 plus x1. So you have a slope of 1. So the corresponding line is the line that you see here. And the smaller equal results in that I'm looking at the space below that line. And I have now several of these inequalities, several constraints, and those give me this region here. Additionally, I have my objective function. This is x1 plus x2, here represented by the vector. So if you look at the coefficients here, this is 1 times x1 plus 1 times x2, and this 1, 1 vector is shown here. And we want to maximize this, so that means we want to find the solution in this purple region, which maximizes this function. So we want to find the extreme point in the direction of c, whatever that exactly means. So this we can look at more carefully. So if you take the orthogonal line to c, then what you get is that any point on such a line, those all get the same objective value. So this is an isoline of the objective function. And now taking the extreme point in the direction of c means that I'm essentially pushing this line as far as possible until I just only still intersect my region, in this case in exactly one point, namely this point 3, 2. So what we have here in terms of terminology, we have the objective function x1 plus x2 in our example, the constraints, so our linear inequalities. We have this set of feasible solutions, which is my purple area here, and then we have our optimal solution, this point up there. Very often we will write a linear program with vectors and a matrix, so then it looks like this. So now we're maximizing C transposed times X. So C is simply the coefficients in our objective function. So this is, in our case, C is 1, 1. our x is x1, x2. And then the constraints are written in the form ax smaller equal b, where A is an m by n matrix. So let me do this by example. Let me for now just write these constraints here. I will say something about the other ones in a moment. So this would mean I put simply my coefficients here, -1, 1, 1, 6, 4, -1. So this is my A, and my B would be, and then the terms that we have here, 1, 15, 10. So I also should handle those first two lines, unless sometimes in the notation you have that separate. Here in mine, we do not have it separate, so we should put it into the matrix A. We have to be slightly careful here. We have a larger equal, not a smaller equal. So to put this into the right form, we have to multiply with -1, then we get -x1 smaller equal 0, minus x2 smaller equal 0, and then we could put this in A as -1, 0, and in B 0, and then 0, -1, and 0. So that is a linear program. So let's run this also through a solver. So this is a Jupyter notebook. What you see here we define our variables. So directly with the bounds. So this is between 0 and infinity, x1 and x2. Then we have our constraints. So for instance, the one x2 minus x1 smaller equal 1. So exactly what we want to have. Our objective function maximize x1 plus x2. And now we can solve it. And we get the solution that we already saw. So an objective value of 5 and 3, 2 as a solution. We can also visualize this. So here I'm using this package GILP, G-I-L-P, which uses Plotly to visualize 2 and 3-dimensional LPs. So here you see exactly the region as we saw it on the slides. The scale is a bit different. And okay, you can look at the iterations of the simplex algorithm. But what we can also see here is the isolines of the objective function. And you see this is the last point where I intersect my polygon, and there I get this objective value of 5. We here saw an example where we have exactly one optimal solution. This is typical, but there are also other cases. So for instance, if I change my objective function here to 1/6 and 1, so now it's a somewhat steeper vector, then you see that this orthogonal line, so the isoline here, is parallel to this side. So if we maximize, the result is that all of these values here in green are optimal solutions. So here's a corresponding example in a solver. So here we've changed our objective function and the objective values. So the isoline is now aligns with a side of this region. Now let's do another example. Let's say we change them to larger equal two of those inequalities. So this is this one here. So instead of the space below, we take the space above. And here, instead of the space below, we take the space above. Then we are in a situation that the intersection of these, they're called half spaces, is empty. So there is no feasible solution. So this is an infeasible linear program. Another setting is the following. So let's say we have again our initial linear program, but we simply delete two of the constraints. So we're deleting this constraint here and that constraint. Then our space is simply the space here below that line. Now, of course, you can go as far as you like in the direction of C. So this is an unbounded LP. Yeah, so we had the case unique solution, solution but not unique, infeasible, so no solution, and unbounded, meaning there are solutions and which can achieve an arbitrarily large objective value. One reason for the usefulness of linear programming is its efficiency. So it's very efficient, both in theory as in practice. So in practice, you would be using the simplex method. It's very fast. So in theory, there's a caveat Its worst case performance is exponential, but that is really more of a theoretical issue. So you can solve very large instances with the simplex algorithm, and there's software for you there to do it. In theory, the linear programming is a problem that is polynomial time solvable. So it's in practice efficient, in theory efficient. The algorithms in both cases are different, but that's not a problem because whatever you need, you can get. Briefly, a historic overview of algorithms, or just also a bit of an overview of the algorithms. So you have the simplex algorithm. It has been around for a long time. It's the most commonly used algorithm, fast in practice, small theoretical caveat. And then you have the polynomial time algorithms. So most notably ellipsoid method, interior point method. Those typically, if you implement them numerically, not that stable, also difficult to implement, and also in practice the simplex algorithm is simply fast. In terms of software, so since the 90s we have fast and stable implementations, in particular of the simplex algorithm. Nowadays, in terms of commercial software, the most popular codes are Cplex and Groby, but there's also lots of open source solvers that you could be using. For the rest of the video, we're going to take a look at a variety of problems that can be solved using linear programming. And we start with a classical one, both classical in terms of how linear programming is applied, but also the problem itself, namely optimizing a diet. And the setting is the following. So imagine you have a burger restaurant, and while your burgers are not very healthy, you want to obviously sell healthy dishes, and your solution is simply to put some greens on the side, and hopefully that fulfills all the requirements to make this dish healthy. And as possible ingredients that we could buy, we have carrots, cabbage, and some old pickles. And of course we want to fulfill some requirements, but we want to do this as cheaply as possible. So here is all the information that you need to solve the problem. So we have our potential ingredients, so the carrots, cabbage, cucumbers, and we're interested in vitamin A, vitamin C, and fiber. So here are the requirements per dish. We want to have 0.5 milligrams of vitamin A, and we could get these from these ingredients. So this is how much milligram we have per kilo. Yeah, so we want to fulfill these requirements by placing these things on the plate, and we want to do this as cheaply as possible. So here we have the prices. So what we do for this, we introduce variables for the quantity of carrots that we're going to have, of cabbage, and of cucumber. Yeah, so x1 is now the quantity of carrots that we're going to place on a plate, measured in kilos, and so on, and as cheaply as possible. It means we're looking at the prices and we want to minimize the quantity of carrots times the price, and so on. Now our constraints are the following. So with the amount of carrots, cabbage, and cucumber that we put on a plate, we want to have at least 0.5 milligrams of vitamin A. So 35 times the quantity of carrots plus 0.5 times the quantity of cabbage plus 0.5 plus times the quantity of cucumbers has to at least be this 0.5. And this is our first constraint. You see exactly what I said here. And then we have further constraints for the vitamin C and the fiber. And that is nearly it, just that all of these quantities have to, of course, also be non-negative. So we cannot put a negative amount of carrots onto the plate, even if we would like to. And this is a linear program, and we can solve it. So here's now the same linear program in the solver. And yeah, you see those are our variables, again, between 0 and infinity. The constraints as given are minimization, the objective function that we want to minimize. And let's run it. So here you actually can see also the solutions it will tell you that you will mostly place cucumbers on the plate. So the pickles, no matter whether you like pickles or not. And the problem here obviously being that they were so cheap that this optimization problem simply decided to give you lots of that. At least, indeed, the additional price per plate is not too much. But one moral here is that you also have to be careful with your modeling. And in particular, the diet problem has a bit of history there. So there is a very nice article from George Danzig on this, where he describes how in the early days of linear programming he tries to use it for the diet problem and wants to simply eat whatever the solution of the linear program is. So he calls his wife, tells her what the ingredients are. Everything seems fairly normal until he comes to the last ingredient for his dinner, which is 500 gallons of vinegar. And the story continues, but you can read all of that yourself if you're interested. So much about the diet problem. Another classical problem, and now a more of a one that is also more important for computer science, is flow in a network. So imagine we want to send data from this node to that node over here. So we have our local network. So we don't store any data in the nodes, but we simply use the links to transport the data. This is how much data can go through such a link. And now we need to determine, first of all, the orientation, for each link, in which direction are we going to send the data, and how much are we going to send. And this we can formulate as an LP. So maybe you pause for a moment, think about how you would do it. So the variables that we're going to introduce, so the choices that we have is how, for any edge, how much data do I want to send over that edge? And I will have a variable for this. So I will have, for every edge, I will have a variable, xuv, which tells me how much data I'm going to send over that edge. And this is in the direction from u to v. So in particular, if xuv would be negative, it means I'm going to send data in the direction from v to u. Now our constraints are that the flow, so my xuv, has to be bounded by the capacity. So if this is u and this is v, xuv has to be smaller equal 4 and also larger equal minus 4. So for an edge, I simply say that the corresponding variable has to be below the capacity and above minus the capacity. And again, minus means I'm going to send data in the other direction. I'll have this for each of the edges. So for instance, AD, this edge here, I have a capacity of 1, so the corresponding variable has to be between -1 and 1. So next we want to model that the inflow has to be the same as the outflow. For this, let's have a look at this node. What does it mean that inflow equals outflow? So this means that if I look at the sum of flows, and I have the edges now directed, so these are directed like this and that and that, then the sum of flows of the edges that go in should be equal as the sum of flows on the edges that go out. This is also correct when some of these are negative. So if this one would be negative, it would be part of the outflow, but it would also count negatively, or then put it here over and then it's positive on the other side. Yeah, so this works also when these variables are negative. So what do we want to maximize? So now we have our constraints. We have to think about our objective function. You have two options here. So you can either say as much as possible should go into the destination, or as equivalently as much as possible goes out of the origin. So let's do that one. So we want to maximize the flow out of the origin. So we have those three edges. So that would be maximizing XOA plus XOB plus XOC. So then the linear program looks like that. So you see the objective function is what we said. Here for every edge we have variable has to be between negative capacity and positive capacity. And for each of the vertices we have inflow equals outflow. and we get a solution. The value of the solution is 4, and we can also read out the variables, and they tell us how to achieve the 4, and this would be a flow that achieves a flow from the origin to the destination of 4. Our next example is as follows. Imagine we have 2D data, so maybe some kind of scatter plot with a linear dependency, and we want to quantify this linear dependency by fitting a line through the data. Now there are different ways of fitting that line. So first of all, we have to decide on what is a good line. So what is most commonly done is least squares method, which works perfectly fine. It minimizes the following sum. So I plug in, so my data points are xi, xy. I plug in xy and xi and xy into this equation for the line, and now I want to choose a and b as to minimize the sum of errors, which is then the sum of squares of these lengths. So if you have extreme outliers, so this might be sensitive to those extreme outliers, but this is not really the argument why we're not going to use it. We're not going to use it because this is not linear, and we want to apply linear programming. So here's something that you can actually solve with linear programming, although it's not immediately clear why. So now we're going to minimize not the squares, but the actual distances from the line. Yeah, so the distance from the line you get as this, because if you have the line, so if you know what a and b, your line equation is, so your line equation is ax plus b. If you now plug in xi, then you get the corresponding point on the line, and then minus yi is exactly the length of that segment, at least if you take the absolute value. Now, what we would like to do, I mean, this here we already have an objective function. If I write this down, I want to minimize the sum of these errors, and these errors are these values, which is not yet an LP because we have those absolute values. So we have to think about whether and how to deal with absolute values in an LP. We can handle this absolute value in the following way. So we take the objective function as we already described it. We minimize the sum of errors, and the errors are now variables. But now we cannot use an absolute value, but what we can do is, so we want to have this EI should be equal to the absolute value. Now we just say larger equal to the absolute value, and instead of saying absolute value, we write the two values that this could have, namely this is a positive one and this is a negative one. So if we would be able to say EI equals the max of these two, then we would be done, but instead we say EI is larger equal both of them, so in particular larger equal the max. So this is what we achieve, but now the objective function takes care of the fact that we actually do not have to say equals the max, so equals the absolute value, but it is sufficient to say larger equal, and then larger equal in terms of those two linear quantities, because then for the optimal solution, because it minimizes the EI or sum of EI, then it will satisfy this with equality. So just to understand this a bit more, how many variables does my linear program now have? I mean, we have all these EI, A, B, XI, YI. Which of these are actually now variables? So the Xi and the Yi, I mean, those are given, those are the data points. But the variables are the A, the B, and then of course the EI. So we have n plus 2 variables, EI, A, and B. And what we've seen in this example is that there are certain mathematical functions that we can still handle in linear programming, and that is the absolute value. You always have to be careful, are we minimizing or maximizing? And depending on that, we can use absolute values. We can min and max behave similarly. So there are some functions that we can handle despite the fact that they're not directly linear. Our next example is separating points with two different labels by a line. So imagine we have data points for rabbits and we have data points for weasels. Namely, we have their weight and we have their shadow area. And now we want to find a line separating those data points. This might not exist, so the first question is, does it exist? Can we solve this by a linear program? So let's say we want to check whether there's a line with all the rabbit points above the line and the weasels below. I mean, if we can do that, then we can test also the other way around. So what this would mean is that for any point pi, so those are the rabbits, if I plug in the corresponding x into the line equation, so I take ax plus b, then I get the y value of the line at that x, and then the y value of the rabbit should be above that. And likewise, for the weasels, it should be below that. So a problem here is that I was now asking for strict inequality, so this is not allowed in a linear program, but we can handle it in the following way. We're going to introduce a variable for separation, this delta. So we add a plus delta here and a minus delta there. And this will allows me to write larger equal or smaller equal here. Yeah, because previously I had larger and no delta, and then if I add a small delta, this becomes a larger equal. Of course, we still need to be careful, so we will say delta larger equals 0. If delta is 0, then the strict inequalities are not fulfilled, but we're going to maximize delta, and then we can see later if the solution gives me delta 0, then there's simply no solution for the strict inequality. And here we already have a linear program, and we're done. So let me also show you this in the notebook. So let's assume we have the data points here given as x and y. So those are the rabbits, those are the weasels. Let me first show the data points as I picked them now. So this is a bit of, mostly should more or less look like on the slides. Yeah, then we can write the LP, and the LP now, yeah, for each data point we get one of those constraints. Now the values of a and b can lie between minus infinity and infinity. We also have the delta, which should be at least 0. And let's call it. And then we get this line, which is indeed nicely here in between. Because we only have 3 variables, a, b, and d, we can also look at this geometrically in the space of solutions. So let's do that. Yeah, so here we get the solution space. And maybe what's interesting, what we didn't observe so far, but what you see now, so this is now I move the objective values, and when I'm maximizing, I'm actually here. So the maximum is actually not one unique point, but it's this line segment here, which, if you think about it, is not that surprising. So let's go back to this example. I mean, we have to be directly between those two. We have to go through that point, but we could still rotate this line a little bit. And this corresponds to getting several solutions with the same delta. So interestingly, if we want to separate this by not a line, but by a parabola, on first sight, you might think this is not possible because this is not linear. But what we're interested in is, okay, we will again have delta, and then the variables are a, b, and c, and delta, and y, and the x squared and x. So the xi, yi are not variables, those are data points. So the x squared here is not a problem at all because it's a square that I'm applying to the data point. So it's very easy to again put this into a linear program. So we want to maximize delta as before, and now subject to, so the rabbits should be above the parabola. So the y data point should be above, and this is now the equation for the parabola. But as you see, in terms of, so a is my variable, here is the coefficient, And the coefficient, as soon as I've plugged in the xi or the xpi, this is a constant. B and a coefficient, C, and coefficient is 1, and delta coefficient is also 1. So it is again a linear inequality, likewise the second one too. Okay, so let's also do this in the notebook with the solver. So here, first of all, my point set, which I changed a bit so I can nicely fit a parabola. And then here you have these constraints as we defined them on the slides. As you see, it's linear in A, in B, in C, and in delta. And you get this parabola here. So what we see by this, the example of this problem, first of all, we can model strict inequalities by adding an extra variable. And also, nonlinear problems can sometimes be solved by a linear program if the nonlinearity is within the coefficients. Next, we have a nice geometric problem. What also makes this interesting is that I think it's not immediately obvious why this can be solved with linear programming, but it can be done so and quite easily. So we have given a convex polygon, and we want to place within that polygon a disk of a radius that is as large as possible. So how do we model this as a linear program? So we should think about what are our variables and then what are our constraints. So the variables, so what choices do we have? So we have to decide where to place the center point. So the coordinates of the center points S1 and S2 will be two of our variables, and then the radius itself. And for the inequalities, we will have to compute the distance for a given center point to the various sides of the polygon, and I'm going to give the sides are supported by lines, so it's essentially computing the distance from a point to a line. We will distinguish between lines that are below, bound the polygon from below, and the lines that bound from above. So we will need different inequalities, I mean mostly just a sign difference. So essentially this boils down to computing the distance between a point and a line, and let's do that here. This calculation obviously is not very important for linear programming, so you can also skip it, but it's also just some basic math. So mostly the Pythagorean theorem and a similarity of triangles. So let's have a look. Let's assume this is our center point. The distance that we're interested in is this distance here. I will call this distance di for line li. So that distance we want to know. The distance that we can easily compute is the vertical distance, because the vertical distance we simply get by plugging S1, so the x-coordinate of the center, into the line equation. This gives me this point, and then taking the difference between that point and the point here. If this is a line bounding the polygon from below, then this gives me S2, so the y-coordinate of the center minus what I get when I plug in the x-coordinate into the line equation. To determine di, we now look at the ratio of di and the length that we just computed, so the ratio of this and that length, and for that we need a similar triangle. And so we find a similar triangle here, but we also find it below here. And in this triangle below, we can easily calculate length, because we know this is a line of slope ai. So if I have a 1 here, I have ai here. I have square root of ai squared plus 1 on that side. And then di divided by the longer length here is the same as 1 divided by this square root here. And with that, we have calculated di. I get that di is exactly this expression. The important part here is my variables are S2 and S1, and this is linear in those variables. So now my linear program is very simple. I want to maximize the radius subject to that these distances are at least as large as the radius that I want to pick. The largest R here gives me the desired radius, and with S1 and S2 I can even immediately place the disk. This also would work in higher dimensions if I have a convex polytope there. So let's also run this problem through a solver. So first of all, we have to define a polygon. I just define it here as by the lines, and I already marked the lines below and above. So this is my polygon in here. And now the solver does exactly what we would expect. So R should be between 0 and infinity. Everything else from infinity, minus infinity to infinity. These are exactly the inequalities that we stated. And now we can plot it. And solve it and then plot it. And we indeed get this disk, which is the optimal disk or the largest disk fitting into this polygon. One small note, if we want to have the smallest disk containing the polygon, a bit of a different problem. So it's no longer linear, but it still can be solved efficiently because it's a convex optimization problem. The last problem we want to look at is the following. We have a paper mill and we produce paper rolls with a width of 3 meters. Now we have orders, and people are not ordering paper rolls with a width of 3 meters, but various different widths. So for instance, we need to produce 97 paper rolls with a width of 135. Now, how do we formulate this as a linear program? So the trick here is that we first have to figure out how can I make such paper rolls from a paper roll with 3 meters. And there are different choices, but we can simply enumerate all of those choices, and that's what we're going to do. So for instance, I can use a 3 meter roll to cut 2 rolls of width 135 centimeters, or I could do one of 135, one of 108, and 42. And whatever is left then in these cases is less than 42, and because 42 was the smallest order or width of an order, then that is simply waste. Yeah, but I can enumerate all of the possibilities of what I can get out of a 3 meter roll. And this now is already sufficient to write a linear program. Now my choices are essentially the cuts. So how often do I want to cut a roll like this? Or how often do I want to cut a roll into 2 of 93 centimeters? So those are my variables then. And with the variables, I need to fulfill the following constraints. So I need 97 rolls of width 135. And now I can look at if picking one, this option once will give me already 2 of those. This one gives me 1, 1, 1, and that's it. So this means that 2 times, and then the variable that I use for this choice, let's say x1, 2 times x1 plus x2 plus x3 plus x4 should be at least 97. Yeah, so here we have it. This is the inequality that I just described. I have this for the other orders as well. And we want to minimize the total number of rolls that we need. And this is this sum up here, simply the sum over all variables. What this would give me as an optimal solution is the following. x1 is this number, x5 and s6. Everything else is 0. Now there's one difficulty. Obviously, I might not want to cut my paper rolls. I want to cut them, but I also don't want to unroll them to get and glue together half paper rolls. So the issue here is that we would actually want to have an integer solution. So we can, of course, get an integer solution easily here by rounding these numbers up. So by using this cut 49 times, this cut 207 times, 198. And this is a good solution because we're only rounding up 3 numbers, so we cannot be too far away from the best possible way of doing it. But there is a better solution, and for that we will need integer linear programming, and we're going to see that in the next video. So what have we seen in this video? Linear programs. So those maximize a given linear function over all vectors that satisfy a given system of linear equalities or inequalities. Any linear program can be written in this standard form, so we're maximizing C transpose times X subject to this matrix A times X smaller equal B. So we've seen plenty of examples. Many problems have a natural LP formulation. Many algorithmic problems can be solved or formulated and then solved as an LP, or as we will see in the next video, as an ILP. We've seen functions which at first don't look linear or are not linear, but which we can still integrate in our linear programs, like the absolute value. We've seen some geometric problems as linear programs, and as the last problem, we've seen this problem of cutting paper rolls, where in fact it would have made sense to do integer linear programming, and as I said, we're going to see that in the next video.